And it says it's recording. Cool. So basic definition of probability. It's a measure in your belief that something will happen. Okay? So somehow we attempt to measure our beliefs. Sometimes that's easy, sometimes that's really hard. So for example, I play games with my family and friends sometimes, and we roll 6-sided die, and I have this belief that I'm just as likely to get a 1 as I am to get a 6. Is that really true? Well, that would involve experimentation to check, like rolling that die thousands and thousands of times and see if, yeah, I got about the same amount of 1s as 2s and 3s and so far. So as far as the measure goes, the general way we do that is by trying to count up the number of ways something can happen and divide by the total ways something can happen. And often we write something like, so it's the measure is a fraction, and it's usually favorable, whatever I'm looking for. And let's call them outcomes, divided by total outcomes. And sometimes we have a very strong belief about it and we go with it. So some examples of our strong belief. And something happening is, for example, flipping a coin. If I were to break out a quarter and flip it and say, okay, you know, heads, you get to do the dishes, and tails, I have to do the dishes. I think there's an equal chance between you and me getting to do the dishes. And so for flipping a coin, the probability of a heads, I believe, is 50%. Probability of heads, I think, equals 1, because there's only one head, the other's a tail, out of 2 total outcomes. Now that's if I believe it can't land on its edge, which is pretty unlikely, but actually, you know, it can happen with some coins. I often abbreviate this with a P for probability, a parentheses for the of, and then some description of the outcome I want. And maybe, like, I assume in this context, we all know H means heads. So you might see notation like that in the book and in the problems. And so I could answer this question in a few ways. I could use the fraction definition, but we all like writing fractions as decimals, so I could write that as 0.5. And sometimes we like percentages, so I could also state it as 50%. And depending on the problem, I usually like the fraction version and I like the percent version, and sometimes the decimal, but usually I'll state it as a fraction and as a percentage. And when you're doing the homework, just pay attention to just what it says. Does it ask for a fraction? Does it ask for a decimal? Does it have a little percent symbol outside the box? So just read the fine print on those. So I mentioned here, again, I keep coming back to this belief idea, and is the probability truly 1 out of 2? Right? What does that really mean? And again, it is a belief. I think the coin is fair. Come on, pen. There we go. But what the heck does fair mean? So fair, in this case, means equally likely outcomes. So in this case, there's 2 possible outcomes. So I could do like a branching tree. A lot of times we draw trees for trying to figure out probabilities, and I could either get a head or I could get a tail. And I believe that there's a 1 out of 2 chance of getting a head and a 1 out of 2 chance of getting a tail. So that's equally likely. Okay. Is it possible to design a coin that flips and you get more heads than tails? Sure it is. Right? Think about toast with butter on it. If you drop your toast, what often happens? Well, often the butter side goes down, which is awfully annoying because then it picks up crap on the floor. But it's that weight difference, right, that happens. So can we count on any situation, the outcomes being equally likely? The answer is no. Most situations aren't fair. We just have a few examples of those that are. A coin is one of them. We believe the coin is fair, meaning I'm just as likely to get a head as a tail. So fair is a very special definition in statistics, and it means each outcome is equally likely. Okay. Is that always the case? The answer is no. I'll show an example of that in a minute. Another example of one of those places we have a very strong belief about something. New page. And let's see, do we just have someone new join us? I thought I saw my screen flash. I'm not sure. I think that's about the same amount of people we had. Is that true, Zoom? Zoom doesn't always let me know clearly. All right. So a second example of that strong belief idea is the one I mentioned earlier, is a six-sided dice or die. Six-sided die. So I have this dice, I roll it, and then, you know, the possible outcomes would be the set of numbers, 1 or a 2 or a 3 or a 4 or a 5 or a 6, and some dice have numbers on them. So I have ones that have the numeral 1 and the numeral 2. Other dice have what they call pips. Those little dots or indentations on them. So just in case someone isn't familiar with dice, if I just search for roll dice, Google will probably roll some dice for me. Cool, thank you, Google. That was very sweet of you. I was hoping to show some pips. Oh, look, they have different size dice I can roll. Oh man, I gotta go back to that. Where'd that go? Oh, back, that was cute. I had not seen, that's relatively new. Google's always surprising me with the things they put out. Okay, so that's a six-sided. There's a four-sided die, which is called a tetrahedron, eight-sided octahedron, and every face has a different number. So if any of you played any kind of role-playing games, you might have seen that sometimes you have different size die. Those are kind of cool. All right, so let's hop over to random.org. I had mentioned this place back in week 1 when we were talking about random sampling. Here they're gonna roll 2 dice for me, and I believe they show them. Yeah, so this is a dice with a die with pips on it. Here's another die with pips on it. So I got a 6 and a 2, and I believe I was just as likely to get the 6 as I was the 2. Right? I have this belief. Is it true? Can there be dice that are weighted, or maybe they're labeled differently? Like I went to Vegas once, not because I gamble, but just because I like the desert, and I bought some cheating dice there, where one dice had only, what was it? Like 5s and 2s, and the other one only had 6s. I think it was. And then there was another pair, same color, that were regular dice. And so you could kind of like, hey, let's play craps, you know, where you roll 2 dice. And if you weren't paying attention, you didn't notice that one of the dice had, you know, all 6s on it. So there's lots of ways to make a die not fair, and from weighting it to just, you know, cheating with the pips or numbers on each side. All right, so we have this strong belief that most die we play with that come in games are fair, and that each of the possible outcomes is equally likely. So each value is equally likely. That is the definition of fair. And so the probability of getting a 1 is 1 out of the 6 possibilities. The probability of getting a 2 is also 1 out of 6, and so on for each of these. And I could make a table of this. So there's lots of ways to display it and play with this, but I could turn this into kind of a histogram, where at the bottom I have 1, 2, 3, 4, 5, 6. And then over here, I have, let's say that's 1/2 up here, or 50%, 0.5. 1 out of 6 is what, more like 17%-ish, calculator time. 1 divided by 6, calculator says it is 0.166666. So if I rounded that, I might call it 16.7%. Usually I like to have 1 decimal with my percent, unless I need more for some reason. So back to my whiteboard here. 1/6 is approximately 16.7%. 0.167, so that's 0.5. 0.1 would be down here. 2, 3, 4, not the best scale. Let's try that again. 1, 2, 3, 4. No, that's too small. Should have whipped out my graph paper, huh? All right, good enough. So then I would say right about here-ish is 0.167. And so if I get a 1 or a 2 or a 3 or a 4 or a 5 or a 6, then because of my belief that these are equally likely, then these all have the same height when I draw my histogram. So that's the column for 1 and 2 and 3 and 4 and 5 and 6. And this is what we called a uniform distribution a while back for histograms. Now what's going to happen when I actually roll the dice and I start counting, right? Am I going to get exactly the same number of 1s and 2s and so on? The answer is no, I'm not. And so I'm going to get like a jagged but relatively uniform distribution. And I could use I could roll a die 1,000 times. People have done that and counted to see what happens. But I'm definitely not going to do that. I got other things to do. So, so the other thing to consider is, reality. So this is based on a belief. Beliefs often aren't real. They're based on experiences which we've manipulated in our heads. So reality, if I were to roll a die, say 1,000 times, what would I see? Well, eek, that's not a very good line. Let's use the line tool. So if I made a histogram of what might happen in this case, so my expectation is, because the probability, oops, switch from the line to the pen, sorry about that. Because, for example, the probability of getting a 1 is believed to be 1 out of 6, then I would expect this 1/6 of these 1,000 rolls to be a 1. So according to the calculation I just made, that would be about 167 out of 1,000. And that is approximately 1/6. Will I get exactly 167? No, I might get 160 or 170. So if we if we break our axis here and we say this is 150 there, and maybe that's 160 here, and that's 170 about there, and that's 1, 2, 3, 4, 5, and 6. I might not get a lot of 1s. Who knows? When you do it, you might get more 1s than me. If you roll the dice 1,000 times, I might get more 2s than 1s. I might get somewhere in between 3s. I might get more 4s. Who knows what's going to happen? So I would expect to see something like this for 1,000. 1,000 is not a lot of rolls. Maybe I'll get pretty close to the same 5s as 6s. Altogether, the heights of these stacks will have to add up to 1,000. So I don't know if I drew them the right size. I was just kind of guessing there. But in reality, if I actually do the roll, I'm not going to get exactly 1/6 of the rolls to come out to 1s. Who knows what's going to happen? Okay, it's possible I could have almost no 1s. It's very unlikely, but weird stuff happens in this universe. So when I look at situations where I actually go watch something happen or make something happen and I count manually, this is called empirical probability. Sometimes it's called experimental probability. When we have this strong belief and we just look at a situation and say, yeah, I believe this is true, like the die here or the coin back there, when I make statements like this based on a belief, then this is called theoretical probability. Theoretical. And the two are related. In the long run, the more and more experiments you do, we expect the ratio from the experiments to pretty closely match the theoretical probability. And that's called the law of large numbers. So it goes for a large number of experiments. Is 1,000 large? Answer is not really. Oh boy, I can't spell experiments today. That does not look right. Holy shit, I messed that up. Oh well, go with it. For a large number of experiments, the experimental probability, that's better. We'll get close to the theoretical. And probability, something with our probability. There we go. And the more experiments we do, the closer we should get. So if we did 10,000, we should get closer to 1/6 of the probability of 1. If we did 1,000,000, we should get even closer. So basically, more experience means you kind of zoom in on the actual theoretical probability. And I shouldn't have used the word actual there because you can't do anything an infinite amount of time, so you can never actually get the theoretical probability. Sometimes you get lucky, but if you roll a few more times, you're going to lose it because it's not going to behave exactly like the theory says. And the theory is just an estimate based on some strong beliefs people have. And I can't emphasize enough the whole belief thing, because sometimes your beliefs can be messed up. So for example, I had a friend who was a magician, and he had practiced flipping a coin so many times that he was pretty good at flicking it at just the right strength, and he could kind of control the height and the number of times it flipped so that he could more often get heads than tails if he was looking down at it when it was on his thumb, and he'd flip for a head. So he was pretty good at manipulating things like that. And there's a lot of people that can do that kind of thing. So be careful. Okay, so some things that might make our lives a little bit harder is that most situations that we try to think about probability are really complex and not easily done. So a super simple example of something that's more complex than we believe it is, here is a rough sketch of me, and I am holding a ball. And I am going to attempt to shoot that ball into this hoop here. All right, so I'm going to take that ball, I'm going to throw it, and I'm hoping that it will go into the hoop. So two things to consider here. What's the probability the ball goes in versus what is the probability that the ball does not go in? So think about that for a second, and then feel free to voice or chat your opinion. Double check the chats here. Where'd you go, chats? Keep disappearing on me. Chats, where are you? Not here. Oh, there you are, hiding way back there. All right, no chats at the moment. All right, I'm hoping for some opinions for somebody. I will move on once I get at least 3 opinions. I need some theme music to play when I'm waiting for replies. Hey, Melinda, welcome back. Sorry I lost your connection. The question is, that's a picture of me standing there about to shoot a ball into the hoop. And I'm wondering what's the probability it goes in versus what's the probability the ball does not go in? Can anyone give me some kind of guesses as to probabilities or some thoughts on the situation?
Wouldn't it depend on how often you practice? I mean, it could be a 50-50 chance, but if you're a really crappy ball player, it could be 1 out of 10.
Yeah, good point. We got, maybe it's 50-50, right? It's either in or out, like flipping a coin. It's either heads or tails, right? There's only 2 options. But again, I mentioned earlier, most situations are not fair. We have a few rare things like coins and dice where we believe they're fair. But has anyone ever really tested a coin by flipping it a million times and see if it's about half heads? Most of us have not. So that's a big question here. Is this fair? And in this case, fair means, are they equally likely outcomes? There's 2 outcomes here, right? It's either in or it's not in, okay? The ball's not gonna balance there. Well, I guess that could happen, but it's pretty unlikely. So let's say there's only 2 outcomes, in or out. So are these equally likely? And let's suppose for a second that they are equally likely, that anybody that grabs a ball and goes to shoot it in a hoop, hey, it's either in or out, 50% chance it goes in, 50% chance it does not go in, right? Well, if that were the case and I was pretty fast and a good dribbler, then I should be able to get on some NBA team. But that ain't the case, okay? Now, there's a lot more than throwing baskets that involves playing basketball, so that's not some kind of judge, but if it was just a free throw contest and you put me up against any NBA player and hey, I'm just as likely to get it in as them. That is not true, right? So this is a situation where there isn't a theoretical probability. So as far as equally likely, we don't know. Probably not. In this case, there is no theoretical probability known. Okay, we just don't know. And so the only way to approach this situation is it has to be approached experimentally. That's why we take all these statistics in major league sports and any sports that people play, high school sports, you name it. We count everything that happens. And then we say, hey, this person has a pretty good batting average, or this person has a great free throw percentage. Okay, so we must experiment and count. Okay, so there's no other choice. So we watch Gary do it 100 times. Okay, so let's say we do 100 experiments. Each experiment consists of an outcome. That outcome is either the ball went in or the ball did not go in, and we count them up. And what's probably going to happen with me is I might get it in about 30 out of 100 times. I'm not a very good shot. And then 70 out of 100 times it ain't going to go in, right? So that would be mine. Super important thing when we do this, whenever you take a look at the possible outcomes, and I have 2 possible outcomes, often we call these simple events. And the book uses, instead of the phrase simple event, they just call it an outcome. And an outcome or a simple event can't be broken down further, right? Ball goes in. There's only one way the ball can go in, okay? It goes in. And the ball doesn't go in. It just doesn't go in. There's only one way that can happen. So the book calls that an outcome. I call it a simple event. And anytime you list all the simple events, their probabilities have to add up to, so if you sum, come on, pen, sum all of the outcome or simple event probabilities. That's always been a hard word for me to spell. Sum outcome probabilities is always 100% because you've accounted for everything that can happen and there's no overlap because they're simple, okay? They can't be broken down further. It's just heads or tails, a 1 or a 2, in or out. If you can't figure out if they're simple or not, then that means there's a problem with the way you're defining those events. All right, another example. Let's go show the desktop for a second. And what was it, Saturday. It was a beautiful morning, and I did some chores and I did some grading, and I thought in the afternoon I'm going to take a break from chores and grading and I'm going to go for a mountain bike ride, and then it just poured like crazy for most of the afternoon, crazy wind. So kind of curious about the weather today. It's beautiful where I am right now. What's it going to be like later? Zip code. Come on, internet, work for me. Do I have to then click it? Hello. All right, this is not going well for me. Okay, well, it's thinking again. Sheesh, okay, forget about you. Let's just ask my question. So if I had actually taken a break to look Saturday at the weather forecast, I might have saw something at 1 p.m. Saturday. There was a 70% chance of rain. What does that mean exactly? 70% chance of rain. Anybody want to chime in with what they think that means? I can give you some options. So I looked this up for Pendleton, let's say, or just tried to, which is where I'm broadcasting from at the moment. And let's say Pendleton looks like this. This is Pendleton. And then what color's rain? Blue. So then it rains, you know, in part of Pendleton. But it doesn't rain right here. So does a 70% chance of rain in Pendleton mean it's going to rain in 70% of the town and 30% of the town gets no rain? Is that a reasonable interpretation? Somebody please say no. Thank you. Okay, so that's not what the probability means. No. Let's see, what else could it mean? %70 chance of rain. It's gonna rain 70% of the time from 1 to 2 p.m. 70% of 60 minutes. So Micah wrote down the same interpretation I did there. Answer is no. That is not what it means either. Okay, so rain is a lot like me shooting a free throw. There's a lot of variables involved, and it is hard to calculate and predict. So some kind of experimental probability had to go on here. So this is not theoretical, it's experimental. And meteorologists, so that's a field that's been around for maybe a couple hundred years, where people actually got practical in trying to watch the weather and see if they can make predictions about it, is where this number mostly comes from. So they have data on similar days. And so one kind of naive way to look at it, so again, this is definitely wrong, that was definitely wrong. One naive way to look at it is they saw 100 similar days in the past, like today or like that day. What do I mean by similar? I mean that the current temperature, the current pressure, the current moisture in the air, the current wind pattern, all those things meteorologists measure. So out of 100 similar days, 70 of those days rained at that time. Okay, given all of the other conditions. So 100 days, same conditions at the same time, or as close as, you know, we could get to the same conditions. 70 times it rained, and 30 times there was no rain observed on the days with the same exact weather conditions. So it's part based on data on similar past days, and it's also part computer modeling also. So they feed all the weather data that's current into the computer, relate that to past, and then they also have the computer run simulations where there's some randomness going on in the simulation, and the computer watches that simulation it's running and says, oh, look, it rained. Oh, it didn't. Oh, it rained. Oh, it rained. Oh, it didn't. Oh, it rained. Oh, it didn't, kind of thing. And they simulate real days based on weather. And if you think, well, how can we do that? Well, if you play video games, if you played video games played, or if you watched any animated movie in the recent several years, there's amazing stuff we can do with computers. And do we get it right? Well, there's a chance, which means there's a chance it won't happen too. So there is no getting it right or wrong when there's so much randomness involved in the system. System is too complicated to say, yeah, this is going to happen. And so the best we can do is we can estimate these percentages. So these percentages are estimates of what might happen. And with estimates, often there's a margin of error and we miss a lot. So that's a tough one, and so most of the stuff we'll look at are going to kind of be somewhere in between the free throw idea and the rain idea. The rain is a wicked complicated problem. The free throw idea isn't that complicated. It just involves patient experimentation. Okay, so bottom line is that very few cases in probability fit this theoretical idea, where we have this very strong belief about something. We can say, yeah, I believe beyond a reasonable doubt that you're just as likely to get heads as tails. Okay? Most situations that arise, it's not that easy. So let's look at some other information. Let me double check my notes if I went over all the basic stuff I wanted to. Where'd my notes go? There you are. Okay, experimental, theoretical. Oh, didn't talk about that. Let's bring that in here. And then some contingency tables. Okay. Some other just basic idea about probability. So bottom line, probability is a fraction. Favorable outcomes over total outcomes. And sometimes we can map out through our belief what the favorable or unfavorable outcomes are. Other times we have to experiment and then count favorable and divide by total. So we have those two options, but the same fraction either way. Whether it's based on a belief or whether it's based on an experiment is the main thing that we have a little tiny bit of control over. So again, since we have a fraction for probability, so the probability of some event, let's call it E happening, is again that favorable over total. Favorable, and favorable doesn't really mean good, it's just what I'm looking for, okay? So for example, I might be looking for what's the probability somebody my age dies from COVID-19. So favorable in that case would be a COVID-19 death of someone my age, right? That's not cool, I don't want to die. So again, don't mistake the way I'm using this word. Favorable just means what am I looking for? It's whatever this E describes over total. Now, you can't have any more than the total because the total is all there is. So the most the favorable could be was exactly the same as the total, okay? Like, what's the probability when I roll a dice that I get a number? Well, let's see. There are 6 numbers. So, okay, there's 6 ways to get a number, and out of 6 ways. So the greatest the probability can be is 1, and 1 is the same as 100%. Okay, so this is the highest probability that exists. You can't have 110% probability. Impossible, okay? Because you can't have more than the total. Total is everything. It could go the other way, right? So the lowest would be you looked for something that just didn't exist, never happened, whatever the total is. Maybe there were 6 possible events. So you could say 0, which is the same as 0%. So that's the lowest something can be. So probabilities have to exist. So probability of some event can be no bigger than 1 and no smaller than 0. So all probabilities have to live between 1 and 0. 0 is the same as 0%. 1 is the same as 100%. You're going to be working with percents a whole bunch this week and in the future. Remember, percent per means divide, cent means 100. So this symbol right here is literally replaceable with per 100. So anytime you see a percent symbol, you can replace it with divide by 100. Okay. So just a reminder about what percent means. Literally means divide by 100. It was invented a couple hundred years ago when people got lazy. They were tired of writing divide by 100. And if you look at the symbol, you can see the divide slash there and the 2 zeros for the 100. Okay, it's a lazy thing that got adopted. All right, some other things about probabilities. The idea of complementary events. And we'll do some more examples. Complementary, come on. Pen's having a hard time keeping up. Events. And this doesn't complement, it's not complement with an I here. I definitely spelled it right. It doesn't mean, my, you look nice today. I love the way you did your hair. Complement means works good together. So like when I got married, my mom said, oh, you guys complement each other so well. It's so cute. That means you fit together. You make a new whole. And that's what complementary event means. Whoa, pen's freaking out. My electromagnetic field's a little nuts today. So if two events are complementary, so let's say A and B are complements, that means they represent all things that can happen. So A could be like an even number, and B could be an odd number. If we're looking at whole numbers and numbers, either even or odd, there aren't any other choices. So like on a dice, the probability of getting an even number plus the probability of getting an odd number, since they are complementary, is 100%, 1. So that means if I tweak this with a little algebra, the probability of an even is equal to 1 minus the probability of an odd. And let's see, does this book use the bar or the apostrophe notation? Let's go, I forgot. Textbook, hopefully you've opened the textbook already. If you didn't, I don't blame you. Last week was pretty damn busy. Please open it soon, take a peek. All right, so that's probably, is it in 3.1? Which of the following best describes you twice in a row? Please go away. And please load. Oh, come on, there you go. Let's see. Click Control F is a nice way to search a page. Complement, okay. They use the prime notation. Got it. So if two events are complements, instead of calling one A and one B, the complement would usually be called A with a prime on it. So that just means the opposite of A. So A is some event, A prime is the opposite of A. And the prime is an apostrophe, so A apostrophe is the opposite. So it's always the case that the probability of A prime, its opposite, is always 1 minus the probability of A happening. And why would I care about this? Well, sometimes the opposite event is easier to think about or count. So this event A might be too complicated, but its complement is way easier to think about. And so what we'll do is we'll calculate the complementary events and then just subtract from 1 to get the event we wanted. And this goes both ways. So I could write it also, the probability of A equals 1 minus the probability of the opposite thing happening. So that's a powerful rule that comes up here and there. Okay, let's take a look at some data I looked up and do some probability on it. Oh, please move over here and show. There we go. So here I have some data I collected on COVID-19 cases recently in Oregon. And I broke the data up into either the person that got COVID was male or they were female, and they were either under 30 or they were 30 or more years old. So you see I have columns for male and female, and I have rows for age breakdown. Why did I pick 30? I don't know, just for the heck of it. So there's no really significance to the years I broke down into. I just wanted only 2 cases. We can see that under 30, there's way less people than over 30. Okay, and then another interesting thing, and this is a whole different topic, is that makes me think, well, how does that compare to the actual number of people that are under 30 versus over 30? Do they have the same percent breakdown? And there's lots of questions that I can ask about this right here. So I'm just going to ask a few questions, word them in a couple of different ways, write down some notation to go with them. So I'm going to copy this into my spreadsheet to play with. This kind of table is sometimes called a two-way table or a contingency table, where I have broken the data down in 2 different ways. And let's add it to new page just in case it wasn't blank. All right, so questions I can ask about this is, and I'm going to say things in words, but then write them in probability notation partly. What's the probability that a female got COVID-19? And I'm just going to write probability female, because all I'm considering is COVID-19 cases. So that's my audience. So probability somebody is female in this group. Well, favorable means you're female. And if I look at this table right here, this shows there were some females that were under 30, some females that were 30 or more years old, and then the total number of females is at the bottom. So there must be 1,449 females. And then over here, if you add the total males plus the total females, you get there were 2,670 cases that accounted for at this time. I think this is as of Friday, maybe, in Oregon. And then if you look at the total under 30 and the total 30 plus, that also adds to the 2,670. So the 2,670 is the total number of cases there, and whatever that comes out to be. Now, this is the answer right there, right? 1,449 divided by 2,670. And you might say, in some math classes, they made me reduce that. Forget about it, right? With probabilities, don't bother reducing. You either leave it as a fraction or you write it as a decimal or a percent. And what I usually do is I start with the fraction if I have straight numbers, and then I turn it into a percent. So I'm going to go to my spreadsheet to make that calculation. And the cool thing about a spreadsheet is it is a calculator. So I can just go in here and type a label like probability female. And then next to it, I can say equals. And instead of retyping those numbers, go away suggestions, I can just go click on them. So grab that number right there, slash to divide, grab that number right there. You don't need to retype them because they're on the screen. Hit enter. Computer says that that fraction is about 0.54269. And usually I like a percent with 1 decimal place. So I would round it to 0.543. And make it a percent. So let's just make that happen here, percent, and then reduce the number of decimals. So I think for most publications, one might see in a newspaper or something I might tell my mom, I might go with 54.3 or even 54, depends on the day. Sometimes we need more, more decimals depending on how remote of a chance there is of something happening. So there are cases where I'll take it to more than 1/10%. So that 3 right there is 0.3%, right? So back in my notebook here, I would say, yeah, this is about 54.3% of the cases were female. So if I randomly select a person who had COVID-19 in Oregon this year, what's the chance that that person I randomly select is a female? The answer is there's a 54.3% chance a randomly selected COVID-19 case is female. Okay, so I can write a sentence that goes with that. There is about a 54.3% chance that a random, the random is important. Oops, randomly selected COVID case is female. Okay, so that's kind of a brief explanation of what that number means. And there are going to be some problems where I want you to explain what a percentage means. All right, let's do a more complicated one. Let's try, what is the probability that a person is female and under 30 years old? Okay, so to figure that one out, I have to look at the table. Okay, so I want female, so I'm definitely in this column. And I want people under 30, so that's this row here. And I'm thinking that this 231 are females that are also under 30. Okay, so that's the favorable thing I'm looking for. So 231 is my numerator there, and I don't say anything else, so I must be looking at all COVID-19 cases, so it's got to be 2 out of 2,670. And then I have to calculate that. And since the data is already in a spreadsheet, I might as well let the spreadsheet calculate it for me. So probability female and less than 30. Running out of room there. To make a calculation, remember you got to start with equals, and then I decided that this group here is the females under 30, and then divide by the total and make it a percent. And then I have to decide how many, oops, wrong bar, wrong place, percent. Then I have to decide how many decimal places I want to go to. Do I want the nearest tenth of a percent, nearest hundredth percent? And the homework will usually have a recommendation on that. If it doesn't have a recommendation, then I might take it out to another percent just to be safe. So if I'm overly cautious here, I might say it's 8.652. But usually I would go with 1/10 of a percent unless I have a good reason to go further. So maybe 8.7. Book, let's write that in. So this is about 8.7%. Okay, and I could write a similar sentence to describe what that means. Let's go to a slightly harder one. No messages in the chat yet. What's the probability someone is female or under 30? Okay, so this one is a bit harder. So we have to do some very careful counting. Let's pull out that right there. All right, so let me see. So I got the female column. So I definitely want females, or I want under 30s. Okay, so well, there are 1,449 females, so that seems like that might be important. There are also 414 people who are under 30. Okay, so I mean, I guess I could add those two numbers together. That seems dangerous. So let's see. Female. Well, let's do some circling here. I definitely want these people. These people are the females. Okay, so 231 plus 1,218 gives me the 1,449. Okay, so I want all those females. Now, some of those females were under 30. Do I forget about these males who are under 30? What does or really mean? All right, so that's a little tricky. There's two kinds of or in the world. There's the inclusive or and the exclusive or. So if my cat came over and said, hey, I want to eat, and I say, okay, kitty, you could have some wet cat food or you could have some dry cat food. Usually when we make a statement like that to somebody, it means you could have the wet or you could have the dry, but you can't have both. Okay, that's the exclusive or. The inclusive or means one, the other, or both. And in mathematics, when we use the word or, that's what we mean. So for this female or under 30, what we mean is we're looking for a person that is female. So if they fit the female description, we count them. We're looking for people that are under 30. So if we see somebody that's under 30, we need to count them also. Now that could include a female that is under 30. So they could meet one description, the other description, or both descriptions. Okay. So if that's the case, then I want this 231 because those are females who are under 30. I also want the females that are over 30 because I'm looking for females, and I have the word or. I'm also looking for anybody that's under 30, including these males right here. So then to answer this question, I want both the numbers in the under 30 row and in the female column without double counting. So it would be inappropriate for me to add these two numbers together because both of those numbers count this 231 and I'd be double counting it. So in this case, my answer would be to take that 183, add it to that 231, add that to the 1,218. Once I get all that added up, then I can divide by the total number of COVID cases, 2,670. So the or is a bit more complicated. So the and is an intersection of a row and column if we have a table. The or is the row and the column together without double counting the overlap. Okay, so that's important. All right, so let's whip out that calculation on the spreadsheet and see what we get. So on the spreadsheet, I got to be careful when I do that. So probability female, notice my use of parentheses on paper, or less than 30. So here, to do that counting for the numerator, I have to put parentheses. If you don't put the parentheses, it's going to get all messed up. And then I just start grabbing numbers I want. I want that number, plus I want that number, plus I want that number. Okay, so I've counted the females. I've counted the under 30s. I didn't overlap anything. And then I can divide by the total number of cases. So that should be the answer right there, 61.12%. Now, the opposite of females or under 30 would be to only grab males that are over 30, okay? Males over 30 and over do not fit this description in any way. So I could just do 1 minus that result. So just to double check that next to it, I could go for the complementary events and do 1 minus. So equals 1 minus. These guys don't fit the description, divide by the total, and then make it a percent. You can see I got the same number. So sometimes there's more than one way to get the answer if you realize there's more than one way to count stuff. If you forget your parentheses, is that a bad thing? The answer is yeah, it is. So if I just tried to say, hey, take the 183 and add it to the 231 and add that to the 1218, and then just go slash divide by, it's only going to divide the last number by that total, and I'm going to get 414, which if you make that into a percentage, you get 41,000%, right? That is impossible. You can't have a percentage like that. All right, I think, it's already after 11. Time flies when you're having fun. Yes, so I just saw that comment there from Justine. Let me address that. There is a formula in the book related to this, and it's in one of the videos. If you just watch the videos and don't read the book, you're missing out, so please read the book. So the formula goes like this, new page. I'll draw a picture of it too. So we've got something like, some situation I'm going to draw by a rectangle. Could be the COVID-19 cases. And then we have one event we're looking for. We'll call that event A. Maybe it's females. We got this other event we're looking for, event B. Maybe that's the under 30. And sometimes these events overlap, so there's something in there, and sometimes they don't, so that could be empty. And the way that works is if I wanted to find the probability of event A or event B happening, like the one I just did, you can't just take the probability of A happening and add that to the probability of B happening, because when you do that, you get some overlap in what you counted. So if I take the probability of A happening, and I take the probability of B happening, the problem is they both count that middle group right there. Oops, yeah, that's fine. They've counted this 2 times. So to compensate, then I have to subtract that double count. So that would be the probability that A and B happening. So that would be like the comment that Justine made. calculate male or under 30, we just say, oh, let's find, or sorry, female or under 30. We just take those total females, so 1,449 out of the 2,670, add that to the total under 30, which is 414. Problem is that double counts that group that are female and under 30. And so then we have to take away the probability, so that 231. Now, since these all have the same denominator, that works out to the order of operations that Justine mentioned in her chat, that she just took the 1,449, added the 414, and subtracted the 231. After she found that, then she divided by the 2,670. Yeah. So any complicated event, there's always going to be more than one way to approach it. And some people just say, well, I just want one. Just show me one way and don't show me any others. Well, then you're not going to be able to solve some situations. And the bottom line is there's just many ways to attack problems, and we have to be exposed to and explore some different ways, because sometimes one is easier than another. So we have a variety of ways to attack these complicated problems. There's somebody asked if the extra practice was extra credit, and the answer is no. I have more than enough things assigned for people here, so the idea of extra credit, extra work on top is not a good idea. But probability is tough. It's deceivingly simple, but counting stuff is hard. So there is some extra optional practice. And just some people need more practice than others. So I was the kind of person who needed more practice on this stuff than my classmates. So if the teacher assigned the odd problems, I would do the odd and the even, and then go back and do some again. So somewhere down here, there's some optional practice problems. Those aren't counted towards your grade. It says there were 30 points, but they're not going to be part of your grade. If you do the homework and you're like, yeah, I get this stuff, no problem. Some people just get it. I was not one of those people. I find probability always hard and challenging. So the optional practice is just a place for you to get more practice. But it does not count towards your grade, so it's optional. So if it says optional, not part of your grade. Okay, so that's it for now. It's more than enough for now. If you have homework questions as you're moving through the practice problems, double check that there's not an answer in the book or the videos. If you can't resolve your answer there, then write to me or post it in the questions about week 5. I already got a couple of questions over the weekend about the practice and the optional practice. I will get back to those soon. But remember, in the practice, there's always that message instructor button. So if you can't get it after a couple of times, let me in there. Don't forget that you do have that message instructor option where I get to see what you were trying to do. All right, take care, do good math. I'm gonna go get back to grading. Wish me luck. Bye-bye.